let us continue with the moment generating function. In the earlier video we have seen we have defined moment generating function, and when random variable x has binomial distribution, how to find the moments of that random variable, that we have seen in the earlier video. Now let us see some of the properties of moment generating function. So suppose instead of phi x, it is x plus a is any constant, okay, and t is as it is any deterministic value. Phi of x plus a, instead of x here it is x plus a. In that case, what happens to earlier moment generating function phi x t? So if I replace x by x plus a, then moment generating function can be obtained. So it is equal to expected value of x plus a into t. So a is constant and t is again deterministic. E to the power at can be taken out because both are non-random quantities, and what is remaining is expected value of e to the power x into t. So since x is random, so and it is expected value of e to the power xt, by definition this is phi xt. By definition it is phi xt. So whenever I replace random variable x by x plus a, if I add constant a into random variable x, so earlier moment generating function gets multiplied by e to the power at, where a is given constant and t is deterministic constant, it is arbitrary constant, t is deterministic quantity. Let us say it is a varying, it is not quantity, it is not constant, it is varying. For different t we get different value, but a is a scalar, okay, e to the power at. So earlier moment generating function gets multiplied by e to the power at if you replace random variable x by x plus a. That is the first property. X is replaced by x plus a, the earlier moment generating function gets multiplied by e to the power at. Now if a is, instead of adding a to the x, if x is multiplied by a, again a is some constant, and again t is deterministic value. So again by definition we can write e to the power a x t. We know that x is random, a is deterministic and t is deterministic, so we can write random variable separately, e to the power x, and this is, instead of t it is at, it is some t prime, t prime. So random variable, if it is scaled by a, then what happens to its moment generating function? In moment generating function, that t gets multiplied by a. So if a is greater than 1, then it gets compressed, and a is less than 1, it gets expanded. So a is a constant which is deciding expansion or compression of the distribution moment generating function, not distribution function, it is a moment generating function. So moment generating function, whether it is to be expanded or it is to be compressed, that is decided by a. So a is a parameter which is constant. Now if you consider x1, x2, xn, n random variables, all are independent, identically distributed. IID means independent and identically distributed. So they have same distribution and they are independent, they are not dependent on each other, and they have same distribution. So if we add like this n random variables, and if we are getting random variable y, naturally if we add random variables we get random variable, and x1, x2, xn, they are IID with their moment generating function is phi x1 of t, phi x2 of t, and so on, phi xn of t. If their moment generating functions are known to us and they are IID, independent, identically distribution function is identical. x1, x2, x3, xn, they may be binomial, they may have binomial distribution, they have Gaussian distribution. If they are discrete, they can have Gaussian distribution, they are having binomial distribution. If Poisson, they can have, okay, that kind of distribution. So phi x1 phi x to t, phi x and t, all they are moment generating function of each of these random variables respectively. And y is a random variable which is obtained by adding all n random variables. So then what happens to the moment generating function of y? Y is addition of random variable. In that case, the resultant moment generating function myt, this is moment generating function of y, is nothing but it is the product of individual moment generating function. So the moment generating function of y is equal to product of individual moment generating function. We can prove this within 1 or 2 steps. So let us prove this, how it is going to be a product function. By expanding that equation, we get this one, expected value of e to the power x1 plus x2 plus xn whole bracket multiplied by t. So value of y is nothing but addition of independent random variable, and they are having the identical distribution. So then this the mean of this can be obtained, that given function multiplied by joint density function. Since y is a addition of all these random variable, so there is a joint behavior of x1, x2, xn which is deciding the y. So since the density function random variables are independent, the density function, this is nth order giant density function, that nth order giant density function splits. The nth order giant density function splits because random variables are independent, and so nth order joint density function can be written as product of individual density function. Nth order density function can be written as product of individual density function, and after splitting this and after this one splitting this and combining each one terms separately, e to the power x1t respective terms combining respective terms, e to the power x1t f1 x dx1 e f1 x1 dx1 e to the power x2 t f x2, here also random variable taking value x2 dx2, and so on. By observing this equation, we can say that this is phi x1, this is phi x2, right? Phi x1 of t, phi x2 of t, phi xn of t. So whenever we are adding random variables, they are independent. Density function splits. Because of splitting of density function, there is a product of moment generating functions, and these moment generating functions, they are in this case they are using same distribution function, because the random variables which we have chosen, they are independent and identically distribution. IID means independent identically distributed. Every random variable has same distribution and they are independent. It means their joint density function can be written as product of individual density function. By using this fact, we can split this integration into n integrations, and each integration is nothing but one moment generating function, and at the end the moment generating function of y is nothing but product of density functions of individual random variable. If we add random variable together, in that case we get product of individual moment generating functions. This is what the property of moment generating function is. So let us stop here as far as moment generating function is concerned. If possible, I will see some of the density functions which are having different some of the density functions like Gaussian, Poisson. If we go with those density function, how your moment generating function works, and how we can find the moments of binomial, how we can find moments of Gaussian distributed random variable, Poisson distributed random variable, or if other distribution function is also there. In that case also, if time permits, we will go with other distribution functions also.